Assalamualaikum girls. I am Shamsunisa from Royal Degree College, Chemistry Department. As we are dealing with Unit 4 General Chemistry, today we'll see Chapter 2nd Rotational Spectroscopy, that is nothing but microwave spectroscopy. In that we'll study about introduction, rotational motion and rotational energy, classification of molecules based on moment of inertia, rotational energies, selection rule for microwave spectra, and determination of bond length of rigid diatomic molecule HCl. Introduction. When microwave radiations are passed through the sample, absorption of microwave radiation causes rotational motion in the molecule. Next we will see about rotational motion and rotational energy. A molecule in space readily moves about its center of mass, in which the center of mass remains same. The distance from the center of mass do not change. However, the equilibrium positions of atoms will change. Such motion is known as the rotational motion, and the energy associated with this motion is known as rotational energy, indicated with E rot. ROT is the rotational, E is energy, that is rotational energy. It is the abbreviation of rotational energy. Now you can see here, we are taking a molecule in which A and B are the atoms present, and in between these two atoms, here we are representing center of mass, and this molecule is making a rotation of 90 degree. Then we will get like this structure. A is going towards the right hand side and B will go towards the left hand side. This structure we will get. And this particular molecule, again it is making a rotation of 90 degree. Then A is going to the denominator, or we can say that A is going downwards and B is coming upwards. This is structure, third structure we are getting. Now again this molecule is showing 90 degree rotation. As a result of that, B is moving towards the right hand side and A is moving towards the left hand side. This fourth structure we will get. Then this molecule again it is making a rotation of 90 degree. Then B is going towards the downward side and A is coming upward side. The essential conditions for the absorption of microwave radiation by the molecule is it should possess permanent dipole moment like HCl, HBr, CO, NO, etc. In other words, all the molecules having permanent dipole moment are said to be microwave active. If there is no dipole moment, that is mu equal to 0, as in H2, Cl2, O2, N2, etc. No interaction with microwave radiation takes place, and those molecules are microwave inactive molecules. When the molecule having permanent dipole moment absorbs microwave radiation, causes rotational motion in the molecule. The region which lies between radio frequency and infrared region of electromagnetic radiation is called microwave region. The frequency of microwave region varies from 1 centimeter to 100 micrometer, that is 10 to the power minus 2 meter to 10 to the power minus 4 meter. The frequency of microwave radiation varies from 3 into 10 to the power 10 hertz to 3 into 10 to the power 12 hertz, and the energy of this radiation will be of 10 to 100 joules per mole. Microwave spectroscopy is useful in the calculation of bond lengths of heteronuclear di and polyatomic molecules through the measurement of moment of inertia I and the dipole moment of the molecules. Microwave spectra is recorded only in the gaseous state. Next we will study about classification of molecules based on moment of inertia. A rotating molecule in space has 3 moment of inertia in 3 directions or in 3 axes, represented as IA, IB and IC. Based on the relationship between these moments of inertia, molecules are classified into four groups. They are linear molecules, spherical top molecules, symmetrical top molecules, and asymmetrical top molecules. First of all, we'll study about linear molecules. So molecules such as HCl, HBr, CO, etc. are linear molecules in which all the atoms lie in the same line. Example, here you can see the example O double bond C double bond S molecule. Here you can see the figure as we are seeing first of all A axis. It is the molecular axis passing through all the atoms and center of mass. Next axis is B axis. It is the axis passing only through center of mass and is perpendicular to A axis. Next, C axis. It is the axis which is perpendicular to both A and B axes and passing through center of mass. When the molecule is rotated about its molecular axis, that is A axis, the equilibrium positions of atoms do not change. Hence, the moment of inertia about this axis, that is IA, is 0. So, we can represent here IA, it is equal to 0. So, here rotation about B axis and C axis is all the same. That is end over end rotation in which the equilibrium positions of all the atoms are changing, for which the moment of inertia in these directions IB and IC is not equal to 0 and are identical. That is IB is equal to IC. Both of them, they are not equal to 0. Therefore, a linear molecule is defined as IA is equal to 0, IB equal to IC, and both of them it is not equal to 0. Next, we will study about second type of molecule, that is spherical top molecule. Here you can see the figure. The molecule in which all the moment of inertia are identical are called spherical top molecules. Example is here IA equal to IB, IB equal to IC. Example, here we are taking CH4, methane, carbon tetrachloride, sulfur hexafluoride. All these are the examples of spherical top molecules. Here we are taking methane molecule. When methane molecule is rotated about A axis, here it is the structure of methane molecule, it is rotated about A axis. So the equilibrium position of 3 hydrogen atoms are changing. That is, the moment of inertia about A axis is not equal to 0. IA, it is not equal to 0. Similarly, when methane molecule is rotated about B axis and C axis, look at this. When it is rotated about B axis and as well as at the C axis. So what will happen here? The equilibrium positions of 3 hydrogens are changing, and hence moment of inertia along B axis and C axis is also not 0. That is, IB, it is not equal to 0 and IC is also not equal to 0. Hence, all the 3 hydrogen atoms are undergoing displacement and all the 3 moment of inertia are same. That is, IA equal to IB and IB equal to IC. Therefore, the dipole moments of each compound is equal to 0 and hence they will not give microwave spectra. That is, they are microwave inactive molecule, we can say. Next, we'll study about symmetrical top molecules. The molecules with 3 non-zero moment of inertia and 2 of them are same are called symmetrical top molecules. Examples of symmetrical top molecules are methyl chloride, trichloromethane, methyl cyanide, etc. Here you can see the figure A axis. We all know that A axis is nothing but molecular axis passing through maximum number of atoms and center of mass. When the molecule is rotated about A axis, the equilibrium positions of 3 hydrogen are changing and the rotation is similar to spinning top. The moment of inertia about this axis is not 0. That is, IA, it is not equal to 0. Then rotation about B axis and C axis are same. End-to-end rotation with the displacement of 3 hydrogen atoms or with the displacement of the 3 hydrogen atoms. That is, IB is equal to IC. Therefore, for symmetrical top molecules, IA is not equal to 0, IB equal to IC. Based on the relationship between IA, IB and IC, symmetric top molecules are further divided into two groups. First one is prolate symmetric top molecules and the second one is oblate symmetric top molecules. Now we will see first of all about prolate symmetric top molecules. The molecules with three non-zero moment of inertia where IA will be smaller than IB and IC. Here we can represent like this: IA is less than IB and IB is equal to IC. Look at this once again. IB it is equal to IC. Okay, IB is equal to IC and both of them are bigger than IA. So here IA is lesser than IB and IC. Example is methyl chloride, trichloromethane, etc. All these are the examples of prolate symmetric top molecules. Next type of the molecule we will see, that is oblate symmetric top molecules. The molecules with three non-zero moment of inertia where IC will be much greater than IA and IB. So here IA it is equal to IB and both of them they are lesser than IC. It means that IC is greater. Example of oblate symmetric molecule, top molecule is boron trifluoride, boron trichloride, benzene, etc. In case of BCl3, 2IA it is equal to 2IB, it is equal to IC. Then fourth type of molecule we will see, that is asymmetrical top molecules. The molecules having three non-identical moments of inertia are called asymmetrical top molecules. That is, IA is not equal to IB, IB is not equal to IC. Example of asymmetrical top molecules are water, methyl alcohol, vinyl chloride, etc. Hence, based on moment of inertia and their relationship, molecules are divided into four groups. What are they? First one is linear molecule in which IA equal to 0 and IB equal to IC. Second one is spherical top molecules in that IA equal to IB, IB equal to IC. All of them are equal. Then in case of symmetrical top molecules, third one, IA is not equal to 0 but IB equal to IC. In case of asymmetrical top molecules, IA is not equal to IB and IB is also not equal to IC. Next we will study about rotational energies. Let a heterodiatomic molecule, that is HCl, HBr, CO, etc. having atomic masses M1 and M2 and bond length is R. Here you can see it is a molecule which is a heterodiatomic molecule. The two atoms are different in this. One atom is showing the mass number M1, another one will show the mass number M2 and the bond length will be what? R. In this case, the moment of inertia along its molecular axis IA is 0 and moment of inertia in other two axes, that is IB and IC, are not equal to 0, which are same with end over end rotation. That is IA equal to 0, IB it is equal to IC. By determining the moment of inertia I, the bond length R of a diatomic molecule can be calculated. By using Schrodinger's equation, it may be shown that the rotational energy level allowed to a rigid diatomic molecule is Ej it is equal to h square by 8 pi square I into j plus 1 in joules. It is our equation number 1. Where I is what? I is called the moment of inertia, either IB or IC. Where IB it is equal to IC. So the moment of inertia, that is I, it is equal to UR square, where U is what? Reduced mass and R is the bond length. So here we are writing the formula of reduced mass, that is U equal to M1 into M2 divided by M1 plus M2. Then what is J in our previous equation? J is called the rotational quantum number, which is an integer, that is J value will be equal to 0, 1, 2, 3 and so on. So here Ej it is equal to Hc by lambda. Now in the next step what we are doing, this Hc we are bringing to the other side. So Ej by Hc we are writing, that is equal to 1 by lambda. So 1 by lambda it is equal to mu bar, that is the wave number. So in place of 1 by lambda, we can write mu bar. So mu bar, it is equal to Ej by Hc. It is our equation number 3. From equation 1 and 3, now we are taking equation 3 main and we are substituting the value of, let's see here in equation 3, Ej. Okay, in place of Ej, we are substituting the value of Ej from equation 1. You can see Ej will be equal to this whole value. In place of Ej in our third equation, we are substituting this whole value. That is mu bar, it is equal to that whole value h by h square by 8 pi squared I j into j plus 1 divided by hc. Hc, nothing is there in the denominator, so we are keeping 1. Okay. This will become reciprocal in the next step. You can see 1 by hc. Then 1 h from this side, 1 h from that side gets cancelled. So what is our remaining equation? Mu bar, it is equal to h by 8 pi square IC into j plus 1. So here the kinetic energies of the rotating diatomic molecules at different levels can be calculated and obtained as follows. Here you can see J value. If the J value is 0, EJ value will be 0 and mu bar value is also 0. J value is 1, EJ value is 2b, mu bar value is 2b. J value is 2, EJ value is 6b, mu bar value is 6b. If the J value is 3, EJ value is 12b and mu bar value is 12b. If the J value is 4, EJ value is 20b and mu bar value is 20b. Here you can see the graph, that is of rotational energy levels of a rigid diatomic molecule. On the x-axis we are taking the value of mu bar and on the y-axis we are taking the value of EJ. So look at this very carefully. This is J equal to 0. Okay. Next one is, if the J equal to 0, mu bar is also equal to 0 and EJ will also be equal to 0. Now, J equal to 1. At that time, mu bar will be equal to 2b. Then if the J equal to 2, mu bar equal to 4b. J equal to 3, mu bar equal to 6b. J equal to 4, mu bar equal to 8b. Okay. Now, you can consider this one 2b minus 0. So, you will get 2b. 6b minus 2b, you will get 4b. 12b minus 6b, 6b you will get. 20b minus 12b, 8b you will get. Okay. So for J equal to 0, we all know that mu bar equal to 0. Here, hence, the molecule is not rotating at all. For J equal to 1, the rotational energy mu bar equal to how much? 2b. And the molecule is rotating with lowest angular momentum. Next, we'll study about selection rules for microwave spectra. In the rotational movement of molecules, the change in the rotational quantum number, that is indicated with delta J, should be 1 unit. That is delta J equal to plus or minus 1. For absorption, delta J equal to plus 1. For emission, delta J value equal to minus 1. Only those molecules which possess permanent dipole moment will give rotational spectra in gaseous state. That is, mu is not equal to 0. What is mu? Mu is dipole moment. In the gaseous state, molecules are free to move and rotate, but in solid state, molecules are very close to each other and fixed in their positions. Microwave spectra will arise from the transition of the system from one energy level to the another energy level, while it is moving in gaseous state. Now at last we are going to study about determination of bond length of rigid diatomic molecules HCl. On absorbing microwave radiation, HCl molecule undergoes rotational motion involving transition from lower energy level to higher energy level. So from the transition, it gives equally spaced spectral lines with a gap of 2b, where the first line appears. The moment of inertia and the bond length is calculated from these spectral lines. For example, in the calculation of the bond length of HCl, the first line is observed at 20.70 per centimeter in its microwave spectrum. So here the 2b value will be equal to how much? 20.70 per centimeter. B it is equal to 20.70 That 2 we are bringing to the another side, so it will come in the denominator by 2. If we are dividing this, we will get 10.35 per centimeter. But B it is equal to h by 8 pi square IC. Okay, here we don't know the value of I. That I we are bringing to the other side. We are rearranging the equation and B is coming in the denominator. So I it is equal to h by 8 pi square BC. Now we are substituting the values. I equal to h value, h is the Planck's constant. 6.625 10 to the power minus 27 divided by 8 into pi value is 3.14. Pi square means 3.14 square into B value just now we have calculated. How much? 10.35 into C is the velocity of light. Its value is 3 into 10 to the power 10. Now in the next step, what we are doing, this 10 to the power 10 we are bringing to the upper side. So it will become 10 to the power minus 10. You can see in the next equation. And in the denominator, what is remained? That is 8 into 3.14 into 3.14 into 10.35 into 3. We are multiplying all these values. So we will get this value in the denominator. Now, in the next step, we are dividing this both values. So we will get 0.I equal to 0.002705 into 10 to the power minus 27, 10 to the power minus 10. We are adding both the values. So you will get 10 to the power minus 37. Or look at this now very carefully. If we are bringing this point one digit towards right hand side, one number will increase here. That is 10 to the power minus 38 we can write. If we are bringing to the another unit, another digit that side, right hand side. So one more unit will increase here. So 10 to the power minus 39. Okay. And one more digit if we are bringing the point to the right hand side, 2.705 means that value will become in 10 to the power minus 40 gram centimeter square. Now look at this formula, reduced mass of HCl. For HCl we are calculating the reduced mass. Okay, it is equal to, the formula is m1 into m2 divided by m1 plus m2 into 1 by n. N is here the Avogadro number. M1 is the mass of hydrogen. Okay, and m2 is the mass of Cl, chlorine. Mass of hydrogen is 1 and mass of chlorine is 35.5 divided by 1 plus 35.5 into 1 by n. N is the Avogadro number. Its value is constant. How much it is showing the number? 6.023 in 10 to the power 23. Now, what we are doing? We are bringing this 10 to the power 23 to the numerator. So, it will become 10 to the power minus 23 and we are dividing this 1 by 6.023 means we will get the value as 0.16603. Now in the next step we are dividing these both values. So you will get 0.97260 into this value into this value. Okay. Then we are multiplying these both values. So you will get at last UHCl it is equal to 0.16148 into 10 to the power minus 23. Or we can write in this way also, 1 point. If this point we are bringing to one digit on the right hand side, one number will increase here, 10 to the power minus 24 grams per molecule. Now, I it is equal to, this formula we are using now, I it is equal to UR square. So, R square we don't know, so if we are bringing R square to the left hand side of equal to, I will go towards, so I divided by, this U will go to the other side. So, I by U, R square equal to I by U. So, if we are keeping R, this square, if we go this side, it will be under root. So, R it is equal to under root I by U. Now, we are keeping the values. R it is equal to under root. What is the value of I? Just now we got the value of I. That is 2.705 10 to the power minus 40 divided by U value. Just now we have calculated. This value we are keeping. Now, what we are doing, we are dividing this both. So, you will get 1.6759 into 10 to the power minus 40 is there. This 10 to the power minus 24. If we are bringing to the numerator, so it will become plus 24. Now, we are subtracting these two values. That is minus 40 plus 24. You will get 10 to the power minus 16. Rest of the things are as it is. Now, we are taking the root of this value. So, you will get R equal to 1.2945 to 10 to the power minus 8 centimeter. And if we are converting the centimeter into degree angstrom, we are writing like this, R it is equal to 1.2945 degree angstrom. Therefore, the bond length of HCl equal to how much? 1.2945 degree angstrom. With this, girls, we have completed our second chapter. Thank you for listening to this lecture.